Good morning, everyone. My name is Dillon Mulroy, and today we're going to be talking about Melange and the next frontier in type-safe web development. If I could click. I am a staff software engineer at a company called OCaml. I've been working in the TypeScript, React, JavaScript, and Node ecosystem for the better part of 10 years professionally. You can find my slide deck at this bit.ly URL or by scanning this QR code. I originally gave this conference talk last Friday at RVAJS, very much designed to be given to a live audience rather than to Twitch, so bear with me. I've tried to adapt it. So my goal today is to pique your curiosity and excitement about OCaml, ReasonML, functional programming, and to demonstrate how they can improve the type safety of our applications. Admittedly, preparing to give this talk at a JavaScript conference and getting ready to pitch OCaml and ReasonML to a conference full of TypeScript and JavaScript developers, a little unnerving. Honestly, kind of felt like a camel in sheep's clothing, if you will. So what is OCaml? OCaml is actually an acronym. It stands for Objective, Categorical, Abstract, Machine Language. If you're anything like me, I know what all of those words mean individually, but together I have no idea. I do not have a strong background in mathematics. I do not know a lot about category theory or type theory or anything like that. And quite honestly, the last time I thought about what OCaml actually stood for, I was shitposting on Twitter. It's only OCaml if it comes from the objective region of France. Otherwise, it's just sparkling, categorical, abstract machine language. So what really is OCaml? The OCaml.org docs describe it as an industrial strength functional programming language with an emphasis on expressiveness and type safety. But how would I describe OCaml? I would describe it as a statically typed language with amazing type inference. We'll dive into the type system a little bit later, but the way it's designed, you have to rarely annotate your types if you don't want to, yet it provides more guaranteed type safety than a language like TypeScript. It's immutable by default with opt-in mutability, so it saves us from the most common bugs in programming, that being bugs coming from mutation. It's blazingly fast. Generally, if you're compiling to native, you're going to be performing in the same ballpark and generally having faster or better performance than languages like Java and Go. And you can also tune it to get close to speeds like C and C++. And in addition, Jane Street has a fork of the compiler right now where they're working on essentially introducing the ability to opt out of garbage collection and having experience closer to Rust. So that's something exciting that's being worked on. It's a pragmatic application of functional programming for the real world. So in the year that I've been working with OCaml, I've noticed that the ecosystem is kind of this interesting mashup of real world engineers and then like programming language academics. And the perspective I have on the language and ecosystem is that over the past 20, 30 years, the combination of those two communities has really driven the language in a direction that's ergonomic, yet has really, really good functional features. The community is top tier. I know many of you in Twitch chat right now are on Twitter and have interacted with the OCaml community to some extent, but since I started learning OCaml, everywhere I've gone for help, whether that is Twitter, the OCaml Discuss forums, the OCaml ReasonML discords, I've been met with kindness, empathy, and eagerness to help. And quite frankly, like every single person has gone so far above and beyond to provide help. It's been astounding. Like it's definitely been the most friendly community for getting help that I've been a part of. And most importantly, it's fun and a joy to write. OCaml has quickly become my favorite programming language. It's made me a better programmer in other languages I write. Some of the patterns and practices in OCaml have bled over to my TypeScript code. So yeah, just enjoy the language. Also, the Twitter memes are pretty damn great. I collected a few last week to throw into this slide. We'll just step through these quick. So what is ReasonML? Put simply, ReasonML is an alternative syntax for OCaml that is designed to feel familiar and welcoming for developers coming from specifically JavaScript and TypeScript, but pretty much any C family based language. It's fully interoperable with OCaml and its ecosystem. So you can have a project where you have a OCaml module that imports a Reason module and vice versa. Every OPAM package or every package in OCaml is accessible to Reason. So basically just one and the same, just a friendlier syntax. It was made by Jordan Walk, who is also the creator of React. And maybe unsurprisingly, JSX is a first-class citizen and built into Reason. So you can just start writing JSX in any Reason file. And as we already mentioned, it is designed to be familiar for developers coming from specifically JavaScript and TypeScript. So what is Melange? I'll give you all a second to read this slide and definition, see if you can pick up on the references here. If you weren't able to pick up the reference, obviously coming from the book and movie Dune, it is the spice from the film and book. But just kidding, only kind of. OCaml's build tool is called Dune, so there is kind of a cute little play on words there. So what really is Melange? Melange is a compiler for OCaml and ReasonML that emits performant, idiomatic, and readable JavaScript. And in fact, it also was partially inspired by a French word which means mixture. Essentially, it's a bunch of tooling from the OCaml and Reason ecosystem coming together to produce JavaScript from OCaml. So let's look at an example of what ReasonML and Melange actually looks like. So if we look here, this is your run-of-the-mill React component in TypeScript, right? We have this card component. It uses a third-party library called Tailwind Merge, which effectively just lets you kind of merge together Tailwind classes so they don't override each other in the wrong way. We take some simple props, nothing too crazy. Next, this is an identical component in ReasonML. You notice that we don't have to have our import up above. We don't need to have our prop type definitions. This should feel somewhat familiar. We've got some weird syntax going on here, like the module keyword and this kind of weird annotation called @react.component and this function called make rather than render. But overall, the JSX should feel very, very familiar. I would hope that any React developer should be able to at least look at this, parse it for a moment, and kind of understand what's going on here. That is the intent of ReasonML. And then if we look, this is what Melange will compile that ReasonML to. So in my opinion, this compiles to very, very readable JavaScript. We get some nice undefined checks, some type safety there. You can see var class name. We check if it's undefined. We give it a string option type, help prevent runtime type problems. And in fact, this JSX runtime, this is what your React components compile to anyways under the covers. Every time I see output generated by Melange, I am kind of blown away. I've joked before that Melange generates better JavaScript than I actually write. So now you may be asking, but why? Why do we need another language that compiles down to JavaScript? We've had things like CoffeeScript, and we already have TypeScript that compiles down, so on and so forth. And to answer that question, I'm going to need to give a little bit more context on me and my background and how I got here, or more specifically, how I ended up as the guy talking about OCaml at a JavaScript conference. So first, let's talk about my journey into functional programming. I started programming when I was roughly 13 years old. I took a programming course in middle school that taught me Visual Basic 6. And shortly thereafter, I found JavaScript. I spent the rest of middle school and a lot of high school tampering around with JavaScript, pretty much being just a script kiddie. Spent some time making World of Warcraft add-ons with Lua. But fast forward to 2014, I land my first full-time professional job and I'm introduced to Lodash. And I fall in love with Lodash. I think Lodash, and specifically the chain API, was the coolest thing since sliced bread. Being able to put in a piece of data to the chain function and then call map, reduce, filter, flat map, and just pass this data through these kind of like immutable pipelines. Like, I just thought it was the coolest thing in the world. Now, if you have any experience working in a Lodash codebase, you will know that it's very easy to overdo it. And I definitely overdid it. So if any of my former coworkers are out there that had to deal with the code bases I left behind, I am so sorry that I've used Lodash. Fast forward to 2015, I was a relatively early adopter of React. I started writing React when mixins were still a thing, and class components very much still have a special place in my heart. But React did something really beneficial for the JavaScript and TypeScript ecosystem, in my opinion. It started bringing some functional programming concepts mainstream, right? All of our components are functions. We compose functions together. We avoid side effects as much as possible. We treat our data as immutable, right? Anytime we need to update our state, we use it through state setter functions rather than directly mutating our state. Fast forward to 2017, and I'm eating lunch at work one day, and I'm on YouTube, and I stumble upon a conference talk from a developer named Lee Byron. Lee Byron was a developer at Facebook, and he gave this conference talk on a library he made called Immutable.js. And to this day, this is still probably my favorite conference talk of all time. It's still aged incredibly well. I highly recommend you check it out. But it dives into the internals of Immutable.js and the persistent data structures that they use behind the scenes. And it still blows my mind. I think it's one of the coolest things. So much like Lodash in 2017, I think Immutable.js is the coolest thing since sliced bread. Immediately introduce it into my company's code base and didn't learn from my mistakes as a junior dev. And again, probably overdid it with Immutable.js. So to my coworkers at Visionist, I am also so sorry for my spaghetti code. Fast forward to 2019, I adopt TypeScript and learn it. I start writing TypeScript full time. I convert all my side projects, all my open source to TypeScript. And I really fall in love with type systems and type safety, and kind of learn the value that having a statically typed language can provide. Around that time, from 2019 to current day, I kind of have changed how I tackle programming problems. Rather than just diving straight in, I generally will start and kind of model my problem domain and my solution, or think about it from the type level first. It's just something that naturally happened, and I really enjoy solving problems that way. Fast forward to 2022, last December, I started a new job at Scalum, and I got hired as a front-end engineer, mostly to be writing TypeScript and React. However, I've been a full-stack engineer my entire career. So if I wanted to continue contributing in a full-stack way, it necessitated learning OCaml. Scalum's entire stack, with the exception of our front-end app, is in OCaml. In fact, we even have a Excel plugin that we have written in OCaml that compiles the JavaScript. So yeah, I started learning OCaml in my free time, quickly fell in love with the language. And as I mentioned, it is now my favorite language, and I would probably pick it up by default for a command line app, a web server, front-end web apps, which we're going to talk about. Just all around a joy to write. So before we move on, we need to take some time to talk about TypeScript. So like OCaml, TypeScript is a statically typed programming language. TypeScript has excellent tooling. In fact, I'd put TypeScript probably in the top tier of languages for modern tooling. We have it really, really good as TypeScript developers. TypeScript can be gradually adopted, right? This is probably a huge reason for TypeScript's success. Back in 2017, 2018, we were all working in plain JavaScript code bases still, and the fact that we could slowly, over time, introduce types to our code bases was amazing. That coupled with things like the Definitely Type repo, where the community was helping build up these giant libraries of types, really helped bolster the adoption of TypeScript. TypeScript enables a better developer experience. In fact, TypeScript was really made from a tooling first perspective, and this enables us to have really good LSP servers and autocomplete in our editors, go to definition, refactoring capabilities, so on and so forth. And most importantly, TypeScript is a vast improvement over plain JavaScript. That being said, and let me take a sip of water here before we deliver the bad news. TypeScript can be cumbersome and complex, right? It can get really verbose. It can get really, really difficult to model some complex types. Like, let's say you are working with an API you don't control, or you want to model a relationship between some complex types that's really difficult. Like, you can get really, really in the weeds with these complex generic types with type mappers and so on and so forth. It can just get pretty exhausting, pretty verbose, and you can spend a lot of time trying to model types. TypeScript is ultimately burdened by JavaScript's warts and dynamism. Because TypeScript chose to be a strict improvement of JavaScript and specifically be a superset of JavaScript, it also is plagued by all of the warts that come with JavaScript's runtime. TypeScript has too many escape hatches and footguns, which can lead to creating a false sense of safety. And ultimately, TypeScript is unsound. And don't just take my word for it. Anders Heilsberg, hopefully I got his name right, gave a keynote speech on TypeScript's type system, which I should mention. Anders is a Microsoft fellow and the lead architect of TypeScript. He gave a keynote at the International Conference of Functional Programming this year. And during part of that, he described TypeScript's type system with the following quote: "I mean clearly, this type system is not sound, and it was never designed to be sound, and gradual type systems aren't. They may be sound in islands, but they're not overall sound." He used this slide to also describe TypeScript's type system. He described it as erasable, gradual, structural, generic, inferable, expressive, object-oriented, functional, and ultimately unsound. Okay, but what does unsound actually mean, and why should I care? A type system is considered sound if it guarantees that a program will not cause certain types of runtime errors, assuming that the program type checks and compiles successfully. So what makes TypeScript unsound then? Well, we have our usual culprits. Obviously, any. Type assertions or typecast using the as keyword. Non-null assertions, effectively telling the type system that we know, or at least we think we know, that data is not null or undefined. And then finally, typecasts via type guards or type predicates and function overloads. Essentially, if you use any of these features in your code base, you are introducing inherent and implicit type unsafety. It creates the ability for human error, and really just amplifies the chances of runtime type problems to crash our programs. Surely then, if we avoid using all these features, we'll have sound and type-safe code. Unfortunately, not. And let's take a look at an example. So here we have a pretty simple account type, right? Let's say we're just building like a login form or something, or a sign up form, and this is our account type. We have a username and an isAdmin flag. Let's say we have a validate username helper. It's going to take in some data that has a username. We're just going to validate that the username has some length. We'll throw an error if it doesn't meet the validation. Otherwise, we'll return our type or our value back out to the caller. Then we just have this pretty simple print record function. We're just going to essentially pretty print all the key values of our type. And then let's imagine this bottom part of the code is our actual application, right? We create a new account, username Dillon Mulroy. We go validate the account, and then we just print the record. We pretty print it, right? So this code successfully type checks, even on the strictest settings of the TypeScript compiler, but there is still a runtime type error. So this is where I'm going to engage with y'all, chat. Can anyone tell me where the actual runtime type error occurs in this code? I'll give chat a good 30 seconds here to try to pick it out. Anyone have any ideas? Yes, Meta. Oh, we've got someone picking it out. It's not read-only. Noom's on the right track. Jeopardy music intensifies. That would have been a great addition to this. All right. Well, Noom was on the right track here. It is this line specifically. We're calling console.log, we're taking the key of our object, and then we're calling trim and 2 lowercase. However, our account type has an isAdmin boolean on it, right? And our print record type is saying we're going to take some record of string. Now our account is not string. Our account is technically, structurally, a record of string, or boolean. So when we hit this line, we're going to try to call .trim.2 lowercase on a boolean rather than a string, and it's going to blow up at runtime. And if we don't have this surrounded in a try catch, this will crash our application. So despite doing everything right with TypeScript, we didn't use any of the escape hatches. We didn't use typecasts. TypeScript still tells us this is all completely fine. This will blow up in our face. And this is completely innocent code, right? Like we could all imagine writing this exact code and not knowing better, and then this blows up in our face. So, all that being said, I still love TypeScript. It has introduced a whole generation of developers to the merits and benefits of static typing and type safety. The TypeScript team is genuinely one of the most impressive teams in open source. The speed at which they ship, the quality of the features they ship, the way they engage with the community, it is 100% top tier and to be admired. It has improved the quality of our applications, code, and experiences for our users. I previously worked at a JavaScript consultancy called Formidable, who has some popular open source. I helped maintain and contribute to popular projects owned by them, including Victory Charts and Urkel. And if you're still not convinced that I love TypeScript, I actively build and work on tsc.mvim, which is a NeoVim plugin to run the TypeScript compiler asynchronously and manage project-wide diagnostics. I'm also working on porting over Matt Pocock's VS Bleep extension TS Error Translator to help give more human readable type errors in NeoVim. So now back to our regularly scheduled programming. So let's take a brief tour of OCaml and ReasonML. We're gonna basically cover these things of the language here. So let's start with ints and floats. So this is gonna look super familiar to TypeScript, right? We have let x equals 6, let y equals 9. We can get the sum, we can get the product. Below we have floats. We see that we use decimal points here. One thing that might stick out is that we have different infix operators here. One thing to call out in Reason and OCaml is that we can't mix and match operators on different types. So if we want to operate on floats, we have to use the plus dot operator or the star dot operator or the other operators that come from with floats. This is part of what enables such stronger type safety with languages like OCaml and ReasonML. Now you may be asking, well, what happens if we do try to add an integer and a float? Well, we're going to get a compile time type error. It's going to say this expression has type float, but an expression was expected of type int, and it's just not going to let us do it. So moving forward, before we talk about tuples, you'll see that I have some comments above these types. This is going to be a common thing I have through the rest of the presentation. I would also note that all of the remaining code samples in this presentation are going to be in ReasonML, just so it's a little bit more friendly and approachable to JavaScript and TypeScript developers. My personal preference is OCaml. Also, the comments above these are going to be type annotations. They are not syntactically required. I just annotated these with the types since generally our types are inferred. So let's jump in. Also, I'd add, if you use the OCaml LSP in VS Code or NeoVim, there is an option that may be on by default that will also add like these type annotations above your types. Just a nice little DevX thing. So what are tuples? Tuples are basically, an easy way to describe them would be fixed length lists, or like a bag of data that can hold different data types. So we could model a date, right? So our date type is going to be int, 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 or we could model an address where our tuple type is string, string, int. We can even alias a tuple type to our coordinate type here. So we'll say our type coordinate is equal to the same type of a int tuple. And then we can create a variable called point. We can say it's 1, 2. The type system will automatically infer that the type of point is coordinate. We also have lists. This is how we annotate the type of lists. You can see list string. We have a list of strings here for names. OCaml ReasonML. We can concat to our list using the at operator. We can also have a list of floats. Again, much like our ints and floats from the earlier slide, we cannot mix and match types in an array. So if you have an array of floats, every member of that list has to be a float. Down below, you'll see our first function in Reason called sum. And if you read that type definition here, you can see that it takes a float, and then we're going to return a float, which we can infer that it's a float essentially by looking at the plus dot operator there in the function body. And then below that line, we have let total. We can see that total is being inferred. That should actually not be inferred as a list float, but that should be just a float. That is a typo on my part. But we see this list.fold left syntax. This function is going to be identical to array.reduce in JavaScript. So we're essentially going to iterate over our list of scores, sum them up, and then get the total. Next up is records. Here we have a song and a playlist. Records are going to feel really familiar if you're coming from TypeScript. They're essentially just key value pairs that are typed. Going to feel similar to JavaScript objects. Here we have a song that has a bunch of keys that have string values. We have a playlist, has an ID named songs, which might stick out. Again, as we saw on the last slide with lists, we can pass another data type to our list type to say like, hey, the type of songs is going to be a list of our song type. So that moves us forward into polymorphic types. Essentially, polymorphic types are just a fancy way of saying generic types. They're going to look exactly like generics and feel like generics in TypeScript, which we'll go over in a second. So using our same song example, let's say we would want to model an API response, and then more specifically, some song API response. So we say type API response, and then it has like this weird paren and this tick A, which we call alpha, and then equals this type definition status code with an int, and then this data, which has the type of A. Again, should have highlighted this earlier. Then we say we have our type song response, and we can use our polymorphic type that we just described. We can pass our song type in, and then we have a song response type. Now this exact same type definition, this is what it's going to look like in TypeScript. So this should feel very, very familiar, right? Rather than using alpha, we use T. We say our data is a T, and then our type song response is equal to an API response of song. So let's move forward into variants, and this is where some of the strengths of OCaml and Reason really start to shine. I think variants are one of the killer features here. So let's say we have this type response, right? Like maybe our response has a yes, a no, or an unsure. We can model that. Or maybe we want to model a DOM event. Maybe we want to model one of the variants of a DOM event is click. And we call these individual variant members constructors, right? So this will be our click constructor. And one cool thing about variants in OCaml and ReasonML is that they can take or carry data, right? So maybe our click constructor or our click variant of the event type carries X and Y coordinates of where our click happened. Same with hover. Or maybe we have a key press event that takes the character type of the key that was pressed. Or maybe we just have a data list constructor called window resize. Next is pattern matching. So variants and pattern matching kind of go hand in hand. We can see here that our handle event function is being inferred to take an event type, which is what we described on the last slide, and returns a unit. So a unit in ReasonML and OCaml is going to be essentially the same kind of type as void in TypeScript. It basically means it's going to return nothing. So here we take our event and then we can switch on event. So pattern matching in OCaml is like, and ReasonML is essentially like JavaScript and TypeScript switch statement on steroids. Rather than just like switching on very simple like runtime like values or expressions, we can essentially like do switches almost at like the type level, right? So we're saying we're going to switch on event here, and if our event is the click constructor, we can pull the data that click constructor is carrying out. So we can pull out the X and Y integer coordinate values, and let's say we're just going to log them to like, Datadog or Sentry or something. Same with hover, likewise with key press, and then recall that our window resize is a constructorless or a data list constructor or variant member. So we just log the window resize event. So my light bulb moment with OCaml and ReasonML came from pattern matching. If you've been following me on stream long enough, you'll know that I've spent a lot of time working on a tool that helps transfer music between Spotify and Apple Music. And as part of that process, I had to write authentication for both Apple and Spotify. Authentication with those two services requires OAuth. And all of this is from the command line. So essentially what happens is we use our tool, and to authenticate, we spin up a temporary HTTP server and we launch the user into a browser, and we wait for the callback from the OAuth service to hit our server. That's what this code is here. So if we look here, we have this switch statement on our request.path. So we can still switch on essentially primitive values. So we're going to say, hey, if the path that this request hit coming into our web server is /Spotify, let's do the next thing. And if it's anything else, we're going to return an error saying invalid path. I thought this was pretty cool. Now this gets even better here. We can switch on the code and the state that we pull off our query parameters. This is basically the data that these OAuth services send back to us. And we can model out essentially very expressively all of the different states that we can be in. So if we get a code and we get state from our query params, and the state equals the random bits that we generated to send to the service, we can say, okay, we successfully authorized, and here's the code that we can use now to make API requests. However, if we get code and state, but our state doesn't match the random bit, which we're calling OAuth state here, if they don't match, then we know, let me go back, sorry about that. Then we know that we're in an invalid state. Or maybe we got a code but not state, or we didn't receive either. right? I just thought this was the coolest thing in the world. It really made pattern matching and variance click in my head, just being able to concisely and expressively model all of these different edge cases with the pattern matching. So next, let's talk about two built-in variant types that are used all over the place in OCaml and ReasonML. That is going to be your result type and our option type. So to start, our result type. This is how we're going to generally handle errors in OCaml and ReasonML rather than raising exceptions or using try catch, right? So we're going to have this result type that has two constructors. One is going to be an OK and the other is going to be an error. We can see that the OK is going to have some generic type OK type, and the error constructor will carry some error type. So effectively, this is what this same type is going to look like in TypeScript, right? Our variants are kind of like discriminated unions or tagged unions in TypeScript. So we have this type OK that has a T, or a type error that has an E, and then we union them together for a result type. And actually, I would encourage all of you to try to use this exact pattern and these types in your TypeScript applications rather than throwing exceptions, just to get a feel for this. This is much safer than unexpectedly raising exceptions, right? We should treat errors as values and effectively handle errors where they can occur. So let's look what it's like to actually use our result type. So right, we have this safe divide function. The type of this safe divide function is being inferred as a function that takes two integers and then returns a result type that has an int for the OK type and a string as the error type. We check if y equals 0. If it does, we're going to return our error constructor with a string saying division by 0. Good call out is that we have implicit returns in OCaml and ReasonML. If y is not a 0, we're just going to do our division and return it as our OK value less any remainder. We can see that if we call safe division with 10 and 2, that our answer result is being inferred to be a result of int string. And then we can use a switch statement on answer result to basically handle that. You can see that this really puts the onus on the caller of code to handle both situations, whether a function is in the error state or whether it's in OK state. If it's an error, we can pull out the error message, print it, or if it's the OK state, we can pull out the integer value and log that or do whatever else we need. So this is going to be a little bit beyond the scope of this talk, but we can also define our own custom let bindings or our own custom let keywords in OCaml and ReasonML. So we can say let OK equal result.bind, and then we can say let.OK answer equals safe divide. And this kind of is going to work similar to how promise, the await keyword, works in TypeScript and JavaScript, right? We can say like await some promise and effectively unbox our value. It's essentially the same thing here, right? We're going to say let OK answer equals safe divide. If safe divide returns the OK constructor, we're going to automatically unbox the integer. Otherwise, if it's the error case, we're going to immediately return from the current scope with the error value. So let's look at our option type. So now Reason and OCaml don't have the concept of null or undefined. We use the option type to essentially express this in a type-safe way. Our option is going to have two constructors or two variant members called sum, meaning we actually have data, or none. Let's imagine we are building some simple HTTP server, right? We have this type app config. It requires a string, and then we can optionally give it a integer port. You can imagine maybe we read in like some YAML or JSON file into this let config struct. Our name is super cool app, and then we do decide to supply the port, and we're going to say it's going to be a sum type of 8081. And you can also see here that ReasonML is correctly inferring our config type to be that of app config. Then we have a function called getPort that's going to take our app config and return the port out as an integer. So we just switch on config.port. If we have the sum variant, we can just return the port out, or maybe if we didn't choose to supply the port number in our configuration and we have a none value, we just return some default port being 3030. Now, I spoke earlier that we have the ability to opt into, I spoke earlier that we have the option to opt into mutability. We can do that in two main ways. The first being marking record types with the mutable keyword. Let's say we have this mutable coordinate type. We can mark X and Y as mutable. Then we make a chords record, which is being inferred to be our mutable coordinate type. And then just like TypeScript, using dot notation, we can say chords.x equals 10, chords.y equal 20. The next way we can have mutability is something called a ref. And if you've used React long enough, you'll know that we have refs in React. That's a way to have basically mutable values that persist through renders. And in fact, refs in React were largely inspired by languages like ReasonML and OCaml. So here we're saying we have let count equals ref 0. The type of count is being inferred ref of integer. We then can use this colon equals syntax to update the reference value of our count. And we can effectively look at the current value of count by doing count.contents. That's going to feel very similar to React, right? I think it's count.current, if I'm not mistaken, in React. We also have some syntactical sugar here. Rather than saying count.contents, we can dereference the value by using this caret sign. Both of those two lines are identical. So next, let's talk about Hindley-Milner. Hindley-Milner is the magic that powers OCaml and ReasonML. It is effectively the algorithm that powers the type inference, the amazing type inference that we get in the languages. So let's demystify it and build a basic intuition for how Hindley-Milner works. And this is where you will all come in again, chat. So we're going to have this function foo. It takes an s gets passed to string.length, and then we have this function bar. It takes an x and y. We call foo with x, and then we add y. So chat, what is the type of s? I'll give you a moment here. Anybody, can anyone infer what the type of s is? It is not undefined. Noom again coming in for the win. It is a string. So how about the type of x? Can anyone tell me the type of x? Yeah, there we go. It is a string. Ooh, Noom got it wrong this time. Not an integer. How about y? What is the type of y? Y is an integer. Good. So how did we figure those out, right? So let's annotate our types with just question marks, right? So we're going to say the type of our foo function is a question mark that returns a question mark, and our bar is going to be a function that takes an unknown and returns an unknown. So let's start with, I'm actually going to turn chat off again real quick. Let's start with s, right? So if we look at s, we see that it gets passed to string.length, right? And we know that by the type definition of the string.length function, it will only ever accept a string. Therefore, we can accurately infer that s must be a string, right? This is going to be super similar to the process that we like implicitly or subconsciously did to figure this out on our own. So let's consider the return type of foo. Again, we're going to look at string.length. We know that from the type definition of string.length, it will only ever return an integer. Therefore, we can accurately infer that foo must return an integer. Next, let's look at x. So x gets passed into foo, And we've already evaluated the first parameter and the only parameter to foo, and we know it's a string. Therefore, x in bar can only ever be a string. So we can accurately infer with certainty that x must be a string. Next, let's look at y. So if you recall back to our slide talking about floats and integers earlier, we know that the plus operator can only ever be used with integers, right? And we've evaluated what the return type of foo is already, right? We figured out that it's an integer. So therefore, we can accurately infer that y is going to be an integer. Again, this is going to be super similar to the same process that we kind of like subconsciously walked through to figure it out earlier. So finally, let's consider the return type of bar. Well, we have already figured out that foo returns an integer, and we figured out that int is an integer, and that the plus operator only works with integers. Therefore, the only possible return type of bar must be an integer. So that's effectively how Hindley-Milner works. Obviously, it goes way more in the weeds. However, this should be enough to build like a simple intuition of how our type inference works in OCaml and ReasonML. So we can also annotate our types in OCaml and ReasonML, and a lot of the times it is definitely worth annotating our types. I would say probably 95 to 98% of the time we can get away with not annotating our types, and the type system will 100% accurately infer our types. Sometimes we do need to give the type system a little help. Those are kind of edge cases. That being said, we often want to annotate our types in other places. Like maybe we have a function that takes some complex types, or maybe we want to use type annotations for documentation, or we want to document the surface of our API with types, right, to help our consumers. There's a lot of instances and a lot of use cases where actually annotating our types is worthwhile, even though we get bulletproof type inference. So let's look at this same example code, but in TypeScript, right? Gonna bring chat back in here. Can anyone in chat tell me what S and X and Y are gonna be inferred as? I'll give you guys a minute again here before I move to the next slide. Does anyone know what TypeScript is gonna infer S, X, and Y as? Well-typed which has it, Meta has it, Lucas has it. Yeah. So TypeScript is going to infer S, X, and Y to be any's. And now you may be saying, Dylan, this isn't a fair example. We passed S to another function that was strongly typed. We passed it to string.length. To that I say, okay, let's create a string length that is annotated. So we'll say string length is only ever going to take a string, and it's only ever going to return a number. What do we think TypeScript's going to infer S, X, and Y to be in this case? Give y'all a minute again. There we go. Yes, we're still going to get any. Because of TypeScript's necessity to be a strict superset of JavaScript, it cannot inherit or perform the same kind of type inference that languages that use Hindley-Milner based algorithms can. Even though all the information is there, there are enough foot guns and loopholes to get out of the type system that we just can't reliably infer these kind of types in TypeScript. So another meme. Let's talk about now Melange specifically, and how Melange can help us have sound and type safe JavaScript. Let me turn off chat again. So specifically, how does Melange work? Well, Melange ships with a couple APIs and libraries for common JavaScript bindings. So we have up first our standard library. So the standard library that ships with Melange is essentially going to be a mirror of OCaml and ReasonML's standard library for compatibility. So you're going to effectively be able to go look at the standard library documentation for OCaml or ReasonML and use the majority of the functions that you find there in your Melange apps. We also have our JS API or library. This provides us bindings to JavaScript APIs such as promise, array, string, JSON, regex, date, null and define, so on and so forth. We also have our DOM bindings for browser APIs. So this is going to provide us with Melange bindings to things like the window, the document, events, local storage, things of that nature. And finally, we have our Node API or Node bindings. So this is going to give us bindings to Node.js's path, file system, buffer, child process, so on and so forth. Now you may be asking, well, what if I want to bind to an NPM package or maybe a JavaScript file that I wrote locally? Well, Melange also offers a featureful binding API via PPX. So what is a PPX? PPXs are OCaml preprocessor extensions, and these are essentially used to modify or extend syntax of OCaml and ReasonML during compile time. If you've worked in a language with macros, this is effectively OCaml's macro system. It's very deeply integrated into the language, the runtime, and the tooling. They're super common in the ecosystem. They pretty much come in two flavors syntactically. They come with extensions and attributes. And if you're coming from the TypeScript and JavaScript world, this is going to be super similar to how Babel works, right? Babel, lets us use ECMAScript features that haven't shipped to the browsers yet, and effectively at compile time, compile these new JavaScript features down into code that's supported for our target browser or runtime. So up first, let's talk about PPX extension nodes. This is going to be a little in the weeds here, and we're going to kind of go through this a little quickly, but effectively extension nodes act as placeholders within our code and are marked with basically this % syntax here. This is going to indicate to our compiler that it needs to be essentially replaced and transformed at compile time. In Melange, these kind of extensions are most commonly used to incorporate elements of JavaScript that are not natively found in OCaml and ReasonML. Some examples are inserting debugger statements, reading global values in scope in JavaScript, creating objects, inserting just straight up raw JavaScript code, which is an option with Melange, or using regular expressions. Next, we have PPX attribute nodes, and attribute nodes in Melange are tagged as this kind of like @attribute name syntax. And it serves as a directive for the compiler or our PPX how to essentially compile our code rather than directly transforming it. You can kind of think as these attribute nodes as kind of changing the semantics of our code rather than like the syntax. So commonly these nodes bridge the gap in the nuances between OCaml and ReasonML and JavaScript, ensuring that language-specific features are accurately represented and utilized in our compiled JavaScript output. So some examples of PPX attributes, and these lists are not exhaustive. I would encourage you to go check out the Melange docs for a full list, but we have mel.get, so that's going to let us do like JavaScript dot notation on objects, set. We have mel.module, so this is going to help us write bindings for import statements to CommonJS or ES6 modules. We have the mel.new attribute, which is going to let us bind to class constructors. And personally, my favorite is mel.return. So for binding to a JavaScript function that can return null or undefined, we can annotate it with mel.return to automatically wrap that null or undefined value in an option, allowing us to have effectively better type safety at runtime. Now let's look at an example of what it's like to write a JavaScript binding. So if you recall from our first slide, we used this Tailwind merge module to help like merge a bunch of Tailwind classes together. And this is the exact binding that I wrote for that code. And this is going to look kind of verbose and kind of scary at first, but let's break this down. So at first we have this mel.module annotation or attribute, and this is effectively just saying this is the JavaScript module that we're binding to. In this case, it's going to be Tailwind merge. Next, we have this kind of even scarier attribute called mel.variadic. This essentially indicates that a function we're binding to is going to take a variadic or just indefinite amount of arguments. An example of this is like where you have a function where you can just keep appending arguments to it with the comma. So Tailwind merge works by passing in just a bunch of strings, and you can just keep on going forever. So next is the external keyword. An external is an OCaml keyword for declaring that a value will interface with foreign code, and that would be JavaScript in our case. Next is merge. This is the name of the value or the variable or the function name that we're actually going to use and call in our OCaml and Reason code. Up next is our type definition. Here we're saying that we're going to take an array of strings, right? It's going to be a variadic array, right? We can keep appending strings forever. And then we're going to return a single string. And then the actual function that we're binding to from the library, right? So Tailwind merge exports this function called TW merge. So this is the actual function that if you looked in the JavaScript source, that's actually exported. So let's see how this looks when we actually use it. So there's our binding, and then we can say let merge classes equals merge. Again, merge is our name that we gave it, and we can just pass in an array of strings here, and it's gonna essentially spit out a single string. If we looked at what the type of this were to be inferred as, it would just be a single string. And here's the code that Melange is going to generate for us. So as we can see, import start as Tailwind merge from Tailwind merge, and then we call Tailwind merge.tw merge. Pretty straightforward and simple. So let's talk about the features coming to Melange in the short term. So let's take a look at the Q4 roadmap. So Hrefs is currently funding the Melange team, and many of the core members work at Hrefs. So there is funding behind this project and this tool. Over the next couple months, they're going to be working on improved compilation and build times, though I must say it's already quite speedy. They're exploring improvements for the developer experience in writing bindings, potentially making it less verbose or less alien looking. They're adding support for dynamic imports. They're always improving documentation. They're exploring the installation of Melange via NPM. They're adding source maps. They're working on contributing back to Reason React to support React 18. And the thing I'm personally most excited for is MLX. So MLX is going to effectively let us write. It's going to be a syntax extension to OCaml that lets us write JSX in OCaml syntax. As I mentioned before, I have a personal preference to OCaml rather than ReasonML, so that will be great for me. So if y'all are looking for resources to learn more about Melange, ReasonML, or OCaml, I would encourage you to check out the Melange docs. There is also a Melange playground where you can see, you can basically paste in OCaml Reason code and see the JavaScript output. And also you can toggle between Reason and OCaml. So if you do choose to learn ReasonML or OCaml, you can paste some code in there and see what the alternative syntax looks like. There is a repo called the Melange Community Bindings. This is going to be our definitely typed repo. So if you're looking for types for some JavaScript library, you can come check in melange-community/bindings. Or if you decide you can't find bindings and you need to write your own, I would highly encourage you to contribute back to that repository. Next, we have the ReasonML and OCaml docs and the Reason docs. And then a member of the Melange community just recently put out a really stellar free book online called Melange for React Developers. Really encourage you to go check that out if you are interested in building web apps with Reason, OCaml, and React. So if you're looking for getting help, as I mentioned, the OCaml and ReasonML community has been stellar in my experience and super helpful. I encourage you to go to the OCaml Discuss forums or the OCaml Discord. The ReasonML's Discord is also where like the Melange team hangs out. And then also I have a Discord for my Twitch chat where people will be more than happy to help. Also, I stream, as you may all know. I stream every Monday through Friday, 7 a.m. to 10 a.m. Eastern time. We're currently working on Create Melange app. This is going to be a command line tool that kind of emulates the same sort of developer experience that tools like Create T3 app or Create V app have. So we're going to be working on that the next couple weeks. So I encourage you to tune in. And one last thing, I know that this presentation was pretty dense and we covered a lot, and I know that just a couple code samples and me, lecturing about the downfalls of TypeScript and the benefits of type safety can't create that same light bulb moment I had when learning OCaml and ReasonML. So I want to put my money where my mouth is. I will be donating to Girls Who Code for participation in the OCaml, ReasonML, and Melange community. So I'm going to donate $25 for every person that creates your first app, beyond Hello World, preferably, to Girls Who Code. $50 for binding or contributing bindings to the Melange community repo, and I'll be doing this up to $1,000. Please send your PR links, repos, or submissions to my Gmail, or really just find me anywhere I am on the internet, and just find me somewhere and get it to me. I'll make sure the donation happens, and I'll start a Twitter thread on Twitter for everyone that donates, and proof of my contributions. But wait, there's more. Donations will also be matched 1-for-1 by Dave Sancho, who is a Melange core contributor who works at Ahrefs, and also my CTO at Scala, Adam Ringland. So we could effectively donate up to $3,000 to a great cause. Y'all could learn something new, even if you don't stick with it. So highly, highly, highly encourage y'all to give Reason, OCaml, and Melange a try. Thank you, and let's make the web type safe together. Do we have, I guess we can keep this up. Anyone have questions while we're here? I guess I can bring up the chat on screen for questions. Thank you. I appreciate it. I appreciate the claps. Oh, that's a great question, Neo-Angelism. So Neo-Angelism asked, what's the difference between Melange, ReasonML, and ReScript, and why should I use one over the other? My upfront answer is going to be ReScript or Melange is going to be a much better solution than just using TypeScript, in my opinion. Both are going to offer you the same kind of benefits of type safety. I admittedly don't know ReScript. I haven't used it, but just to briefly cover this because it can be confusing. So ReScript is what BuckleScript was back in the day. BuckleScript started as a project that originally compiled ReasonML to JavaScript. At some point in time, they rebranded from BuckleScript to ReScript, and then also chose to deviate away from the OCaml and basically away from the OCaml and Reason ecosystem. So they're off making tooling and a runtime that is attempted to be closer and more familiar to the JavaScript ecosystem. So fast forward a couple years, and I would add that because they deviated from the OCaml ecosystem, they don't get all the benefits of the tooling and stuff from the OCaml ecosystem. There's some exciting stuff coming from multi-core that's coming into Melange. That being said, ReScript is still an amazing project, and I totally think you should try ReScript too. I just have a preference to the OCaml and ReasonML ecosystem, and I think what the Melange team is doing and their vision is really compelling and exciting. So fast forward a couple years, the Melange team wants to essentially go revitalize the original vision of BuckleScript and forks it and brings it back together with the OCaml and Reason ecosystem. So that's basically what Melange is. It's a fork of BuckleScript that is trying to take it back to its roots and make it more closely tied to OCaml and ReasonML and the ecosystem and the tooling. Agent Smith asked, do you have any openings at Melange? So Melange is not a company, Melange is a tool. I would encourage you to go check out all the docs and resources I had in this slide. In fact, let me link this slide deck to chat. You can learn these technologies and build something, build something, learn it, and send me a link, and we'll make a contribution to the charity. Liquid Phase asked, is Melange a compiler? Would it be possible to integrate GPT into it? Actually, yeah, I forgot to call this out in this slide, but there is a custom GPT on Chat GPT called Melange Mentor. So this is seeded with the Melange docs, so you can come in here and ask questions about Melange, OCaml, Reason. You can have it help you write type bindings, and this is gonna basically be your AI assistant to writing Melange code. So TypeScript equal fake types, ReasonML, OCaml equals real types. Yes. Let's see here. I do have a question though. Is ReasonML just an alternative syntax for OCaml, or is it another language? Yes, ReasonML is simply just an alternative front-end syntax for OCaml. You can actually even interop the two languages in the same project. I have tried JS of OCaml. So JS of OCaml is another tool that's a little bit older in the OCaml ecosystem, and it works the compilation process a little bit different. It is not going to have as small bundle sizes as Melange, but actually that Excel plugin I talked about that we built in OCaml at work and compiled with JavaScript, we use JS of OCaml simply because at the time it started, Melange wasn't fully released at a 1.0 version yet.